Hey everybody, welcome back to Solution Chemistry. Today we're going to be doing concentration of ions. Hope you guys are doing well and staying up on everything, maybe enjoying the Harry Potter games as well. We've been doing some Kahoots and online challenges, and some of you are doing an amazing job. Some people haven't logged on at all, and that's fine. If you don't want to, that's totally your call, but it is lots of fun. Okay, so today's lesson's pretty short. It's actually pretty straightforward. Having a calculator would be handy. We're going to be working on concentration of ions, and it's one page in your notes package that I sent you if you were able to print those off. And if not, you can just do these on a sheet of paper as well. It is 1, 2, 3, 4 questions. So pretty short lesson, and they're pretty straightforward. The last one's a little tricky. This section is all about being able to write a dissociation equation for an ionic compound and being able to do some unit analysis. So solving for certain units. Anyway, you'll see as we go through. Hopefully you grab onto this and go, hey, this is easy, and the assignment's pretty short as well. All right, so first question, what is the amount concentration? So amount concentration means moles per liter of sodium and chloride ions in a 0.30 mole per liter solution of sodium chloride. So what that's saying is we have a solution of sodium chloride at 0.30 molar or moles per liter. That's the concentration. So the question is asking you, what is the concentration of the ions when this thing dissociates? Now I'm going to balance it. 1 Na plus for every 1 Cl minus. Okay, so it's a 1-to-1 ratio. So a lot of students, when they look at this and in their heads, if they're going to predict the concentration of the Na plus, and they're going to predict the concentration of the Cl minus, lots of students think that they should cut this in half because it's breaking into two parts, right? If I take a chunk of something, a crystal of salt, and I break it into two parts, I should have half as much. 0.15, 0.15. Okay, makes sense, seems logical. Let's see if the math supports that answer. So here's how you would solve this. The concentration of Na plus, I'm writing too fast, it's making a mess. Okay, concentration of Na plus aqueous is, so this is like, let's just pause for a second. This is basically a balanced dissociation equation. So it's like a balanced chemical equation. So really what we're doing here is stoichiometry. So we are looking for the concentration of Na plus, and we have concentration of NaCl. So start with what we have. Let's just put a question mark there because we don't know those. We have 0.30 moles per liter. Capital M, remember, is the same as moles per liter. So 0.30 moles per liter of NaCl. So here's where the stoichiometry comes in. We're going to use the molar ratio. And we're writing what we're looking for on top. We want to know the Na plus, and we want to cancel out the NaCl. And these coefficients are 1 to 1 to 1 for this equation. So my NaCl's cancel out, and I get 0.30 molar or 0.30 moles per liter of Na plus. Interesting. Okay, what about Cl minus? Concentration of Cl minus. Again, stoichiometry, start with what we have, what we know. We are given 0.30 moles per liter of NaCl. And again, we're using our molar ratio from the balanced equation. We are looking for the chloride, so 1 Cl minus. We're going to cancel out that NaCl. 1 NaCl. Okay, those guys cancel out, and we get 0.30 moles per liter of chloride. So let's go back to our original statement up here. So when NaCl does break apart, it doesn't split in half. It's actually the same, 0.30. 0.30 molar. Okay, interesting. So we'll look at one more question, then I'm going to make a little analogy for you guys. Okay. So this one's a little trickier. So what is the amount concentration? So again, we're looking for moles per liter of aluminum ions and sulfate ions in a 0.40 mole per liter solution of aluminum sulfate. So let's start with our dissociation equation. Al2SO4 3 dissociates in water. So what are the ratios of the ions? We're going to get how many aluminum 3 plus? Correct, 2. So when that breaks apart, we get 2 Al3 pluses. And how many sulfate ions? 3 SO4 2 minus ions. So these become our molar ratios. I'll put them in red. 1 Al2SO4 3 breaks apart into 2 of those and 3 of those. Okay, so now the question says we have concentration is 0.40 moles per liter, or capital M, of Al2SO4 3. What would be the concentration of aluminum? What would be the concentration of sulfate? Now, if you're really on the ball, you can do this in your head. I'm going to do the stoich, and you can make a prediction right now as well. What is the concentration of those ions? So stoichiometry, concentration of Al3 plus is, start with what we were given, 0.4, oh, it's messy. Okay, 0.40 moles per liter of Al2SO4 3. And when this dissociates, it gives us 2 Al3 plus for every 1 Al2SO4 3. And again, we can cancel those out. So it's 0.40 times 2 divided by 1. 0.80 mole per liter. Concentration of Al3 plus. Now, can you predict the concentration of SO4 2 minus? Looking at the aluminum 3 plus. 2 aluminum 3 plus form, 3 SO4 2 minus. Started off the same. Our molar ratio is now 3 sulfate ions produced for every 1 Al2SO4. And again, those cancel out. 0.40 times 3 is 1.2, and I'm doing 2 sig digs. 1.2 molar, and it's SO4 2 minus. And up here, this was Al3 plus. If I write down everything that is left in the equation, so we get molar Al3 plus, and here we get molar SO4 2 minus. So unit analysis, we're solving for those units. Okay, so the analogy I was going to make to this is if you think about a peanut butter sandwich, 2 slices of bread, and some delicious, what color shall we go with? I'll go yellow peanut butter in there. Maybe it's a mustard sandwich. Lovely. So if you had a mustard sandwich and you were going to break it apart, one mustard sandwich, how many? So students would look at this and go, I want you to break this apart into the bread and the mustard. And some students would go, well, then I'm going to get 1/3 mustard and 2/3 bread. No, actually, you're not. You're going to get 2 slices of bread plus 1 glob of mustard. So this is where our ratio comes in. One of these sandwiches makes 2 pieces of bread and 1 piece of mustard, a total of 3 parts. Just like up here, this thing makes a total of 5 parts. So you really do need that balanced equation dissociating into ions before you can do any of the math. I'm going to show you a quick little simulation of this as well. I did a little online one. I'm going to put the link to this if you want to try this on your own. Is this the right one? Yes, it is. Okay, so see if this will work for you guys. So what I did is I added NaCl. This is our first example. So solid chunk of NaCl, and it was 0.41 mole per liter NaCl, and you can see that we get 0.41 moles of Na, 0.41 moles of Cl minus. It's the same. I'm just going to back that up for a second and pause it. Oops, not quite far enough. And so I can't really highlight them in the top right corner, but it's showing you 41 moles of Na plus 41 moles of Cl minus. Okay, now I move to a trickier example. This is the aluminum sulfate. So Al3 plus, SO4 2 minus. So here's the crystals about to hit the water, and you can see each crystal, if you could zoom in, is made of 2 aluminum and 3 sulfate. 2 aluminum and 3 sulfate. So when it hits the water, our ratio is, wait till we get a nice whole number here. So our cation, our Al3 plus is 60, and our SO4 2 minus is 90. So 60 to 90 is a 2 to 3 ratio, 2 aluminum for every 3 sulfate. So even when you take a big chunk of crystal and put it in water, you are still getting that same ratio. 2 aluminum for every 3 sulfate. And I think in that video it was 60 to 90, which still maintains that ratio just like we're getting here, 0.8 to 1.2, 2 to 3. So this is what stoichiometry does for us. Okay, so far so good. 2 down, 2 to go. We went easy, medium. I think we got another medium coming up, and then a challenging one. Oh yeah, there's our nice neat example from the textbook. Man, if I could write that neat, well, I don't know what I'd do. I'd be a textbook, I guess. Okay, third example. So this one is a little trickier. I'm just going to enlarge this a bit. Determine the amount concentration of barium and hydroxide ions. Okay, so again, we're looking for the moles per liter, or the molar, same thing, of barium ions and hydroxide ions. Okay, so it looks like the last question. The only difference is they didn't give us the concentration of barium hydroxide. Instead, they gave us the mass and the volume. So first of all, I'm just going to write down the dissociation equation. Just like stoichiometry, you always start with a balanced equation. So BaOH2 dissociates into 1 barium 2 plus and 2 hydroxides. Okay, so we've got our balanced dissociation equation. Now the problem is we don't have the concentration of this. So we got to figure that out. We have the mass and we have the volume. So if you have the mass and volume, you're going to need the molar mass. So I'm just going to put off to the side capital M of BaOH2. That means, it's funny that they use capital M to mean moles per liter. And when it's in front of a formula, it means molar mass. So the molar mass of barium hydroxide is 171.35 grams per mole. Okay, so now we have its molar mass. We can start on our stoichiometry. So first thing we're going to do is figure out the concentration of BaOH2. And we're looking for moles per liter. So here's our moles. So let's flip this thing and put moles on top. Moles over 171.35 grams. Okay, we got our moles. We need to get rid of the grams. Here's how we'll get rid of the grams. So that goes on top, 5.48 grams. Okay, grams are gone. So now I have my moles, but I need per liter. 250 mil, if I convert that, is the same as 0.250 liters. If you need to do the math, you always divide milliliters by 1,000 milliliters to get 1 liter. Okay, so now where do I put that liters? On the bottom so that my units work out as moles per liter. Okay, plug that into your calculator and you get a concentration of 0.128 moles per liter. Okay, so now the question is just like the other ones. We now have this concentration, 0.128 moles per liter. Okay, so now we can figure out the concentration of the two ions pretty quickly. Concentration of barium 2 plus is, we start with what we know, 0.128 moles per liter of BaOH2 times, what are we looking for? Barium 2 plus. 1 barium 2 plus for every 1 BaOH2. And it works out to be the same, 1-to-1 ratio, 0.128 molar, barium 2 plus, these cancel out. Okay, OH minus. Let's make a prediction. What's the concentration of hydroxide ions going to be? Barium was 0.128. Hydroxide will be double that. It's 2-to-1 ratio. 0.128 molar BaOH2, and we're looking for hydroxide. It's 2 hydroxides for every 1 BaOH2. Cancel those out. 0.128 times 2 is 0.256 molar hydroxide ions. And I should clean these up and put aqueous in there. Aqueous in there. Okay, so on a scale of 1 to 4, the first question I'd give a difficulty of 1. The second one a difficulty of 2 because it was a 2 to 3 ratio. This one I would give a scale, I would give it a 3 out of 4 because you had to calculate the concentration first. And that was this section right here. Oh, why did it not give me the blue that I just chose? Okay, you're seeing my savvy skills here, not so savvy. Oh, I know what I had to do, touch that. Okay. Sorry. Okay, so that was the extra level of difficulty. Do this first, then go down and calculate the concentration of the ions. So now we're going to move to a 4 out of 4 on the difficulty scale. So don't panic. You can do these. It's a little trickier. You got to do more thinking. So challenge question to finish today's lesson. All right, so what's happening is we're working backwards on this question. What mass of magnesium bromide must be dissolved? So we're looking for mass. Magnesium is a 2 plus, bromide is a 1 minus. So that's the formula for magnesium bromide. So we're looking for mass of magnesium bromide. Must be dissolved to make 1.5 liters of solution with a bromide ion concentration of 0.30 moles per liter. That's a big question. Okay, so how do we solve this one? What do we know? We have the concentration of bromide ions. We can work backwards to get the concentration of magnesium bromide. Let's start with our balanced dissociation equation, MgBr2 breaks apart into 1 Mg2 plus, 2Br minus. Okay, so we have this concentration. So we're going to use stoich to work backwards because this is a balanced equation. So what is the concentration of MgBr2? If we solve for the concentration of MgBr2, we can get the mass. Okay, so start with what we're given. 0.30 moles per liter of bromide. And we're looking for MgBr2, so we write that on top. 1 MgBr2. We want to cancel out the bromides, so we put the 2 bromide on the bottom. Okay, bromides cancel out. We're going to get the concentration of MgBr2, which is 0.30 divided by 2, 0.15 moles per liter is the concentration of MgBr2. Okay, so that's step number 1. Now we have the concentration of MgBr2, we can get the mass of MgBr2. Here's where we use unit analysis. We're looking for the mass, so the units would be grams. There is nothing in this question that has grams, but because we know it's MgBr2 and we're looking for the mass, we can get the molar mass of MgBr2. And I've already calculated it. 1 magnesium and 2 bromium is 184.11 grams per mole. And I put that in the wrong spot. It should be down here. 100. Oh my gosh, messy. My parents saw this. My dad would be giving me crap. He was always on my case in school about my messy printing. Grams. 2 of my 3 daughters have neat printing, and one of them is just like me. And I never give her trouble because I get it. Okay, so I've got my molar mass. Now, I just plugged it in here, but the question is, did I actually plug it in correctly, or do I need to flip it? So we are looking for the mass in grams. So there it is. So yeah, I've got it in the right spot. I've got grams on top. I just have to get rid of moles. So where do I put moles? Where do I get? Here it is. Moles per liter. 0. Whoops, wrong one. Darn it. That's the concentration of bromide. And I need the concentration of MgBr2, which is this guy. 0.15 moles per liter. Remember that capital M is the same as moles per liter. And so I'm writing this in here so that I can cancel out the moles. Now I still have liters to cancel out. And here's my liters. Let's change colors. So do I put it on top or bottom? Top. 1.50 liters. So you can see how we're solving by units, canceling out all these units. So when the units all cancel out, we're left with grams. And we're solving for MgBr2. And if I wanted, I could have put in here 1.5 liters of MgBr2. And then I would have that unit. So 184.11 times 0.15 times 1.50 works out to be 41.4 grams. And you go back to the question, it's 2 sig digs, 41 grams. Wow. So that's a 4 out of 4 on the difficulty scale. Hopefully you followed along and that wasn't too painful for you. So that's it for today's lesson. Short and sweet. And your assignment is written really large. Textbook, page 212. It's 3 questions, 17, 18, and 19. And I'll put the answers in this Google Classroom for you to check. And tomorrow you're going to get an assignment and a quiz to wrap up this section of the chapter. And that'll be due tomorrow night. So you got Friday all day and evening to work on that and get it handed in to me. And then early next week, we're wrapping up chapter 5. And well, most of next week, I think we wrap up chapter 5. And then we're moving on. Chapter 6 is our last big one. 7 and 8 are pretty small. So we are going to finish a little bit early. So awesome. Kudos to you guys for working hard to stay with me and get things done. Okay, take care, and we'll see you guys tomorrow.